All right, we're going to keep working with our right triangle trigonometry. All right, so now instead of just having this on the coordinate plane, we can look at right triangles anyhow, anywhere we want to look at this. So, right triangle trigonometry. So before those other problems that we did in the last section in 9.5, it kept saying things like in standard position, in standard position. We don't have to be in standard position anymore, right? We can be in whatever right triangle we want to work with. So if I have this right triangle, I don't know, I'll just throw one down here. All right. If this is my right triangle, I can have theta over here in this corner. Now, the big deal with our right triangle trigonometry is we have to look at what am I going for, right? Like what am I trying to say? How is this relationship with theta? That's our right triangle trigonometry. Instead of just going x and y, we're looking at this as opposite and adjacent. Then if this is a right triangle, the side that is always, always, always across from the right angle is called a hypotenuse. All right? So when I have this right triangle trigonometry, it doesn't have to necessarily be set up like this. Right? That's what we talked about in 9.5. If we have a triangle in standard position, then I know that this is going to be my y, this is my x, and then we can work with that. Well, knowing that concept, that's how we set up our right triangle trigonometry. So sine of theta for our right triangle trig is going to be opposite over hypotenuse. All right, cosine of theta is going to be adjacent over the hypotenuse, and tangent of theta is going to be opposite over adjacent. Some of you out there right now are screaming, so, ka, toa. That's our common mnemonic device for right triangle trigonometry, SOHCAHTOA. And it's just a mnemonic saying sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And opposite goes with sine, adjacent goes with cosine. Tangent is sine over cosine. I mean, everything connects, guys. If you have those basic identities down like we talked about at the very beginning, you have to know those because it always correlates. If I were to have this in standard position, look at what's happening here. In standard position, my opposite is my y value over r, so y over r. That's the relationship with 9.5 that we just covered. Now, here's the beauty of right triangle trigonometry. It doesn't have to be in standard position. That is amazing. I'm going to go with a different color here. I'm spicing it up, guys. We're spicing this up. Let's go a little purple. So here, if I have, let's say, alpha, right? Whatever, some angle, it doesn't matter. Across from alpha is going to be my opposite if I'm looking across from alpha. Next to alpha is my adjacent. Across from that right angle is the hypotenuse no matter where I'm looking at that other angle measurement. Do you see what's going on? Pretty sweet, right? So if I have this top angle, it doesn't have to be in standard position. I still have opposite over adjacent, no problem. If I have this angle on this side, I still have opposite and adjacent, no problem. I'm using these words. Opposite is pretty obvious, but do you guys know what adjacent? Adjacent, the definition of adjacent is just next to. So I didn't think about that, but you may or may not know that. So if I'm looking at this theta, the side that is next to this means adjacent. Across from it, opposite of the triangle, across the whole triangle, that is my opposite side. All right, SOHCAHTOA. That is the basis of all right triangle trigonometry. It does not have to be in standard form. It could be anywhere you want it to be, and then you're going to get your angle measurements. All right, we're taking it off the grid. We're going off grid here, people. Okay, let's do this thing. Here's example 1. Find the values of sine A, cosine A, and tangent A. I should write that word first. Find sine of A, cosine A, tangent A, given this right triangle. So I'm just drawing it out. It's one that was in the book here. So this is a right triangle. Here is C, here is A, and here is B. This side length is 24. My hypotenuse is length 25. And the side length CB down there is 7. So if I'm looking at my sine of A, if I have sine of A, that's this angle up here. This is my A. Meaning across from A is the opposite. Next to A is my adjacent. And of course, the hypotenuse is always that hypotenuse. Okay, so sine is opposite over hypotenuse. SOHCAHTOA, right? SOHCAHTOA, SOHCAHTOA. So my sine of A here is going to be opposite over hypotenuse. 7/25. That's it. I mean, that's literally all there is to it. Cosine and tangent. Oops, this is A, not theta. All right. So cosine here is adjacent over hypotenuse. Tangent is opposite over adjacent. And that's the deal. Just for fun, the example doesn't tell us this, but just for fun, let's go ahead and do cosecant, secant, and cotangent. What is the cosecant of A? Yes, it's just a reciprocal. 25/7. If you know SOHCAHTOA, you know them all. That's the moral of this story. So, if I have secant, what's that? Good, 25/24. And cotangent? 24/7. If you know SOHCAHTOA, you know everything else. All right? Cool. Cool. Okay, so with our unit circle, let's start making some connections. We kind of tried to make some connections before, but with the unit circle, so I'm a unit circle fan, so I'm just going to put that right on out there. All right? But with your unit circle, you also have special right triangles is what they're called. So you can do all of your trig with special right triangles if you want to, or you can do it on your unit circle. I'm going to focus on the unit circle because that's what makes the most sense to me whenever I look at this. But I want to show this to you because I want you to see what's also happening. If you have this equilateral triangle of length 2 and you split it in half, when you split this in half, then this 60 gets split into a couple of 30s, and then I still have 60s over there, but I make that right triangle split in the middle. And if I split it in half, this also splits into 1 and 1. But I have this right triangle. With this right triangle now, you can use Pythagorean theorem in order to come up with this inside value. And when we do that, you see that you get the square root of 3. All right? So whenever you do Pythagorean theorem, you get the square root of 3. Now, if you do SOHCAHTOA, So if you like this and you want to memorize that triangle, you can. The same thing that's happening right here. If you want to memorize this triangle, you can. Whenever you're looking back through that. I want to show this to you. In our unit circle, right? So here's our unit circle. Here I have 30 degrees. And up here, all the way up here, I have this 60 degrees. We know from our unit circle that our coordinate point here at 30 degrees, I'm hitting, well, if I drew it correctly, I'd be hitting my y-axis here at half. And over here, I have my coordinate point. If I had drawn my unit circle as an actual unit, I would be hitting at 1/2 square root of 3 over 2. So we just know those values, but look at the connection. The sine of 30, SOHCAHTOA, opposite over hypotenuse, opposite over hypotenuse. The sine of 30 is 1/2. You can also get it from 1 over 2. Do you see that? Same thing. The cosine of 30 is adjacent over hypotenuse, square root of 3 over 2. I just want to point this out to you because I want you to see the connections here between these two values. The unit circle and right triangle trigonometry. Same process to do these values. So what if I have this? Oh my, that's even worse. Here, up here at 45 degrees, I know that this is, I've said before, it's 1 over the square root of 2. Or you can write it as, if you rationalize that denominator, the square root of 2 over 2. Both of those are the same. But look at what's happening. If I have this 45 degrees, opposite over hypotenuse is 1 over the square root of 2, rationalized. Here, if I have adjacent over hypotenuse is 1 over the square root of 2 as cosine. Sine is opposite. Same thing, guys. So whether you look at your right triangle trigonometry, here, your special right angle, your right triangles, or if you go and use your unit circle, you're going to come up with the same thing. Pretty sweet, right? Okay, let's do this example. Example 2 says, find all 6 trig function values for 60 degrees. So I know I'm doing the sine of 60, the cosine of 60, the tangent of 60, the cotangent of 60, the secant, and the cosecant. So you know that you can do this as sine. If you want to look at this, the sine of 60 degrees up here is right on the unit circle, square root of 3 over 2, or 60 is opposite over hypotenuse. And you're going to get your square root of 3 over 2. Do you see that? I'm going to zoom in here just a little bit to make that a bit bigger, hopefully. I should have written those down further, I guess. The cosine here is the same thing as adjacent over hypotenuse, or you can look at it right there at that 1/2. The tangent is opposite here over adjacent. All right, so opposite over adjacent is going to be the square root of 3, which is the same thing as the square root of 3 over 1. Or, whenever you're looking at this, it is at 60 degrees, you have the square root of 3 over 2 divided by 1 over 2. The 2's cancel, and you see you get the same thing. Right? I'm just trying to make connections for you. So right triangle trigonometry, your unit circle, that's all making these connections. Once you have these 3, you have everything else. That's also why SOHCAHTOA works so nice, because you get through tangent and then everything else falls in. Cotangent is that reciprocal, 1 over the square root of 3. If you rationalize that denominator, you get the square root of 3 over 3. Secant is the reciprocal of cosine. If this is 1 over 2, secant is 2 over 1. Cosecant goes with sine. So this would be 2 over the square root of 3. If you rationalize that, you get 2 square roots of 3 over 3. I'm okay if you leave it like this, honestly. It's not going to bother me. I think my math lab wants you to go ahead